Hello, this is Ingo Schranz. I'll be your general chemistry teacher for the second term. And we jump right in with the first chapter, which is chapter 11 in the Tro book. It's entitled Liquids, Solids, and Intermolecular Forces. Notably missing here are the gases. And if you recall, in the first semester, we had an entire chapter on gases. And the reason we have gases is because there are no intermolecular forces holding molecules together. And since the focus of this particular chapter is intermolecular forces, forces between molecules, this chapter it does mention gases, but for the most part, it deals with liquids and solids and the forces holding them together. This is actually a pretty nice, interesting picture. It is taken in space on a space station. You see an astronaut here who looks at a water bubble, right? And so, as you can see, the water molecules are held together to form this ball. There's no gravity, of course, acting on this bubble, so it's floating, right? But there are still forces forming a perfect sphere, which is what this is, of course. And so we ask ourselves, what is it that holds these forces together? And what is it that makes it spherical as well, right? So we've got a perfect ball here. And so those are the kinds of questions that will be answered in this particular chapter. So just as a review, we have three phases. We have solids, liquids, and gases. Of course, the solid, as you can see here, the molecules or atoms are held together very tightly, and they're rigid. They don't move. And so the example they're showing here is water. If you single out one of these molecules here, you can see there's a red sphere connected to two uh, white spheres. So this indicates that this is water H2O, which is a covalent. And that's something that you need to remember and review, covalent and ionic bonding, in order to understand and appreciate this chapter in its entirety. This is a water molecule, and as you can see, they're perfectly ordered. They're and arranged in a three-dimensional ordered fashion, and they're rigid. And so this would be the solid. And as we know, water freezes at 0 degrees and it boils at 100. So at 0 degrees and below, we have a solid. We also have a density of 0.917, which is actually less dense than that of a liquid. And so this is really unique for water. It is actually usually the case that when you turn a liquid into solid, that we have a higher density, but not the case for water. It's an exception. So it actually expands as a solid, which also explains why ice floats on water, because it's less dense, and that normally would not happen. Again, this is unique to water molecules. And of course, if you are between 0 and 100 degrees Celsius, then the water will be a liquid, which is the state that we're familiar with, right? The water that comes out of the faucet is a liquid. And so most of the time, water is a liquid. And so the density is 0.998 grams per milliliter. So here the units are grams per cubic centimeter. If you recall, 1 cubic centimeter in the case of water is equal to also not just in the case of water. 1 milliliter is the same volume as 1 cubic centimeter. A cubic centimeter is just a centimeter by a centimeter by centimeter. And for water, it also happens to be exactly 1 gram, 1.000 grams. So that would actually imply that the density would be 1.00 grams per milliliters. Okay, so two significant figures, that is actually true here. So the way I've written that, if you rounded that up. And then if you heat, so we have these intermolecular forces holding water molecules together, and you probably remember what that force is called, right? It's called a hydrogen bond, which is nothing but a dipole-dipole, strong dipole interaction. We'll talk about this in more detail. Okay, so, and then as the liquid, we now have molecules that are still held together, but they're mobile. So we know that that if we pour a liquid into a different container, the shape of the liquid will be equal to the container, whereas the solid will not do that. I think I have a nice picture for that on the next slide. But so if you heat that to 100 degrees, like any amount of water at normal conditions, 1 atmosphere, right? That hydrogen bond will break, and those molecules will no longer stick together, and they'll fly apart, and they can go in straight lines until they hit another object, like the wall, or the wall of a container inside of a balloon, the wall of that balloon, right? And so then they'll be projected at an angle, and then when they bounce into each other, they also get deflected. So that's gases, and see, that's why we can't see water molecules, right? Imagine a pot of water that you're boiling. Initially, you can see when it's boiling, you can see the steam, but after a while, that steam just dissipates, and you can't see individual molecules. And that's because they're just too far away and they're too small from each other, so we just can't see them. So this is what happens at a certain temperature when you stick just enough thermal energy into the system to break that intermolecular bond. And so the distance that's shown here between these two molecules is actually much further than it looks. So the distance between these molecules, whether that is helium gas or water gas or propane gas, is so huge that the molar mass doesn't matter, that the molar volume at regular temperature and pressure is actually 22.4 liters. Now, the reason this is not 22.4 liters in this particular case is because we are talking here about exactly 1 mole of water, right? If you remember, there are 18 grams per mole for water, and so that also translates at a density of 1. It translates to be 18 grams, and so it's larger than that because we're not at STP. STP is standard temperature and pressure, and so that would be at 0 degrees Celsius. Now this is at 100, right? So it's going to occupy a larger volume, and and plus it's not an ideal gas anyway. So that's just in a nutshell the parameters for water. And so to just summarize the density, shape, and volume of gases, liquids, and solids in general, whether this is copper metal you're melting or vaporizing, or water, or anything, any other material, that in the gas phase the length density is always low because the molecules are far apart. The shape is indefinite, meaning it's not even confined by the container. It can go anywhere. It's mobile. And the volume is also indefinite. And the intermolecular forces here, this is really important, is weak. For the liquid, we have moderate, or but much stronger than those in the gas, because there's basically none in the gas phase. And in the liquid, we have, of course, it takes the density is much higher. The density between solids and liquids is about the same. If you go back to the other slide, you can see that here, right? The density is not much different between the solid and the liquid. It's just more mobile and not confined to a definite shape, right? And that's the difference here between solid and liquid. Solids have a definite shape, and the liquid has an indefinite shape, meaning it will take the shape of the container. Okay, same with volume, and then of course the intermolecular forces are strong in the solid. Okay, so intermolecular forces, as is defined here on the bottom, are the attractive forces that exist between molecules and atoms, right? So we have, if I draw out the Lewis structure for water, for example, if you remember, there are 2 covalent bonds and 2 lone pairs. Right, of course, the line here represents 2 electrons forming a bond, and so this is an intramolecular force. It's a covalent bond, right? And the intermolecular force would be the force between a second molecule. And so if you draw water, and I draw it on the side because we know there's a difference in electronegativity between oxygen and hydrogen. Electronegativity is something that you need to remember from the first semester So go look it up if you don't remember. But that's the ability of an element to draw electron density towards it, and oxygen is much stronger than hydrogen. So you have an electronic pull towards the oxygen, right? So oxygen here, as we indicate with a delta partial charge, has a partial negative charge, and the hydrogen, which is more electropositive, has a partial positive charge here, right? So which creates a dipole. So what that means is if you look at the hydrogen oxygen bond, you know, that line is really an electron cloud where the electrons are between, you know, they're moving between these bonds. Of course, it's much cleaner for us to look at a line between hydrogen and oxygen, which just indicates that, okay, this is a covalent bond. There are two electrons between oxygen and hydrogen. But this particular electron cloud is distorted towards the oxygen because the oxygen pulls electrons closer to it, right? So it really looks more like a conical here, right? So I'm a very bad artist, but you get the idea. And so that creates that partial negative charge on that oxygen and a partial positive charge on the hydrogen. And so now we can have an interaction. So this is a strong dipole, and we would normally call that a dipole-dipole interaction. But because hydrogen is involved, we call that a hydrogen bond. Okay, hydrogen bond. And so that is the strongest force, intermolecular force between molecules and atoms here. Again, the definition is important. Intermolecular force are attractive forces that exist between molecules and atoms. Okay. This is just another illustration to contrast solids, liquids, and gases. And I don't think we need to say too much here. You can clearly see that the solid has a confined shape and it will not take up the space of the container. But when those forces are loosening, then these become more mobile, and so the liquid will take the shape of the container. Okay. We can, of course, we can change the phase between by sticking energy between two different phases. We can go from solid to liquid by sticking heat into it, right? So therefore we are putting some thermal energy into this, and we're loosening the forces so they become more mobile. And so for that we have this illustration here. So this, if you stick heat into solid here, we can melt it. So this right here would be melting. So if you melt a solid by sticking heat to it, and of course if you remove heat, if you're cooling it, you can go from liquid to solid, and so that would be called freezing. And so of course melting and freezing occur, of course, at the same temperature. In this particular case, it's at 0 degrees Celsius, but they're just a reverse process, right? So melting occurs when you stick heat into the solid at 0 degrees, going up higher, and freezing also occurs at 0 degrees, coming from the liquid as heat is removed from the system. Probably are also familiar with what happens when you stick even more heat into the system here. So if you add even more heat, you can then evaporate that. So this is evaporation. Right, so if you're boiling water, you're evaporating it. You may not be familiar what it's called going from a gas to the liquid. That's called, it's not deposition, it's of course a condensation. That slipped my mind here for a second, that word condensation. And I was actually thinking ahead of there's actually a process that can occur that goes from gas, and it's shown here, from gas or from solid to gas and from gas to solid. And then there's also something going from solid to gas, which is on the next slide. So let's just go to it. So we actually can go from the solid straight into the gas phase, which is this here. And that's called sublimation. All right, so this is dry ice here, and you may have used, if you do some hunting, and a lot of you guys do here in this region, do some hunting. You have probably bought some dry ice to keep your venison cool. And so dry ice is carbon dioxide, and it will not melt. It will go straight to the gas phase. And so that's called sublimation. And the opposite process is called deposition. So if you have water gas, for example, it can go straight from water into the solid. And you see this sometimes in the freezer. You see some ice that is depositing from the atmosphere, or better yet, on a cold morning, if your windshield has ice on it and you have to scrape it, like right here, that's from a process called deposition. This is the water molecules that lost its momentum right when they are moving very fast in the gas phase, but some of them that are slowing down, and they hit that windshield and they can deposit then on a surface. And so we have to on certain days and scrape the windshield. So those processes are called deposition and sublimation. So that's just vocabulary. So the chart we just looked at was for water, but it applies to many other materials. And so here we have three different molecules, compounds, propane, which you should identify as having only nonmetals, meaning this is a covalent compound here. And it's also nonpolar because the difference in electronegativity is very low. So carbon-carbon bonds, of course, are completely nonpolar, and there's just a very little difference between hydrogen and carbon, but it's not strong enough to lead to a dipole, whereas water, of course, is a polar covalent compound here, right? So this is polar covalent, as we've discussed before. Again, we have two nonmetals, but the difference in electronegativity is towards oxygen, mentioned this earlier. And then finally, we have an ionic compound here. Ionic. All right, we have a metal and a nonmetal. Instead of sharing electrons, as you recall, the electropositive element, sodium here, completely transfers its electron to the chlorine, turning the chlorine into an anion, chloride, and the sodium into a cation, sodium cation, right? And so those are held together by electrostatic forces. And I'll come back to that in a minute. So propane is a gas at room temperature, water is a liquid, and sodium chloride is a solid. And so that solely has to do with the intermolecular forces holding molecules or atoms together, especially in the case of sodium chloride. The molar mass has not much to do with that, with the phase that a molecule is in here, right? So if we have no intermolecular forces or very little, then we would expect that to be gas, which is, of course, propane you're familiar with. We can use that to propane gas grills. It's great for it. It's got stored energy, so we can use it for combustion and cooking our food. All right, so let's just stop here, and then when I come back, we're going to look at the different intermolecular forces that hold different molecules together, including propane, because there are some forces that can hold propane molecules together.